In the previous theory video we studied consonance and dissonance between pure tones. In this video we will study consonance and dissonance between complex tones produced by musical instruments, which are made up of combinations of a large number of pure tones. As for pure tones, the basis of this study is the article Tonal Consonance and Critical Bandwidth by Plomp and Levelt, whose link is given in the description. We will use the tones produced by a ukulele to generate their spectra in order to visualize the pure tones that form them and to identify which of them generate dissonance. To do this, we will organize the analysis in tables, which will allow us to have a clear idea of the origin of consonance and dissonance in the sounds produced by real instruments, knowledge that will be very useful in the study of harmony. The fundamental result obtained by Plomp and Levelt for the case of pure tones is the one shown on the screen. This result shows that for the case of pure tones the consonance is related to the critical bandwidth. To apply this result to the analysis of consonance in the case of complex tones produced by musical instruments, it is important to take into account the following observations. Starting from the unison, for which there is maximum consonance, a rapid decrease in consonance is observed until maximum dissonance is reached for a frequency difference of about 1/4 of the critical bandwidth. Maximum consonance is again obtained for frequency differences exceeding the critical bandwidth. The fundamental result presented by Plomp and Levelt for the case of complex tones is found in section 3 of their article. These authors assume that the total dissonance corresponding to complex tones can be considered the sum of the dissonances between the pure tones that constitute them, so they use the scale on the right of this figure to calculate the total dissonance. They acknowledge that the assumption that dissonances can be summed is speculative, but they consider it a reasonable assumption as a first approximation, and that it can be used to illustrate how the consonance between complex tones depends on frequency and the relationship between frequencies. The result is given in Figure 11 of the article, which we reproduce next. The names of the intervals have been added, in blue. It is important to note that in this figure the lowest frequency used in the intervals is 250 Hz, that the peaks shown correspond to a just intonation, but that the frequency axis corresponds to an equally tempered tuning. The value of 6 on the dissonance axis is consistent with the fact that Plomp and Levelt made their calculations with the first 6 harmonics of the tones used. In this channel we have used as the base frequency of our presentations the one corresponding to the reference A4, which has a frequency of 440 Hz. We will also use this reference in this video. In addition, we have so far only used the Pythagorean tuning and the equally tempered tuning based on the A4 in our videos. To give an idea of how the results may vary if a different tuning than the just intonation is used, a table is provided next comparing the frequencies corresponding to these tunings over the octave from A4 to A5. In this table, we will refer to the 440 Hz frequency of A4 as the fundamental frequency F0. The first column associated with each tuning corresponds to the ratio of each note's frequency to the fundamental, the second column to the value of this ratio, and the third to the frequency obtained by multiplying the fundamental frequency by this value. We will now indicate on this table the intervals considered by Plomp and Levelt. In just intonation, which is the method used by Plomp and Levelt in their consonance graph for real tones, the intervals are defined in terms of the relationship between the frequencies of the harmonic series produced by the instrument's sound. Thus, in this graph, we have the octave interval, 2:1, corresponds to the ratio between the octave and the first harmonic, 2F0 divided by F0 equals 2. The major sixth interval, 5:3, corresponds to the ratio between the harmonic fifth and third, 5F0 divided by 3F0 equals 1.67. The perfect fifth interval, 3:2, corresponds to the ratio between the third and second harmonics, 3F0 between 2F0 equals 1.5. The perfect fourth interval, 4:3, corresponds to the ratio between the fourth and third harmonics, 4F0 divided by 3F0 equals 1.33. The major third interval, 5 to 4, corresponds to the ratio between the fifth and fourth harmonics, 5F0 divided by 4F0 equals 1.25. The minor third interval, 6 to 5, corresponds to the ratio between the sixth and fifth harmonics, 6F0 divided by 5F0 equals 1.2. Note that the frequency differences between notes of the same denomination are less than 10 Hz. In the video tempered chromatic scale published in this channel, the use of this scale is justified based on this fact. In it you can hear the difference between the notes of this scale and the notes of the Pythagorean chromatic scale. The description includes a link to an article with quite complete information about the different tuning systems. Música y Matemáticas, Sistemas de Afinación, Music and Mathematics, Tuning Systems, by Javier Luque Ordóñez, available in PDF at this link. The difference in the degree of consonance and dissonance between tones produced by instruments with just intonation and instruments with tempered tuning can be heard in the videos of experiments conducted by Luis Nuno, professor at the Polytechnic University of Valencia, Spain, whose links are given in the description. Remember that the basis for studying consonance between complex tones in this video is the results for consonance between complex tones published by Plomp and Levelt. Next, we will repeat the graph summarizing these results. Also remember that we intend to use the 440 Hz A4 as a base, so we will need audio recordings and spectra corresponding to this tone. To develop these concepts, we will focus on a detailed study of the consonance and dissonance of the perfect fifth interval, so we will need the spectra of the real tones A4 and E5. The concepts thus acquired will be applied to calculating the consonance and dissonance of other intervals. We will obtain the audio recordings of these tones from the musica.com website, whose link is provided in the description, since on this site you can later experiment with intervals using the sounds of a guitar and a piano. We believe that what is presented in this video is sufficient for you to understand how consonance and dissonance are generated for complex tones produced by musical instruments. Once you have assimilated the basic concepts, you will be able to perform experiments that will help you consolidate what you have learned here. We will begin by studying the spectra of A4 and E5, but before moving on to that, it is convenient to have, as a useful reference, for octaves of the chromatic scale that begins on A4 and ends on A8. To verify that the graph obtained by Plomp and Levelt conforms to what we observed in practice, we recorded, in wave format using the Audacity program, the sounds of the ukulele notes A4 and E5 provided by the note finder on the musica.com website. We also used the Audacity program to generate the spectra of these tones. The result for the complex tone A4 is shown on the screen. The amplitudes, A, of the spectrum components are given in decibels, which are calculated using the formula shown above on the right. To obtain the amplitudes on a linear scale, the inverse formula is applied. To the right of the spectrum is shown the harmonic series, multiples of the fundamental frequency, that generate it. The frequencies of these harmonics are indicated for the just intonation, column JI, and tempered tuning, column TT. If we take into account that each reduction of -20 decibels decreases the amplitude of the sound by a factor of 10, we can draw the limit for which the amplitude of the harmonics of each of these notes is less than 1% of the amplitude of the fundamental. This significantly reduces the number of harmonics that appreciably affect the consonance, which is also reinforced by the fact that you have perfect consonance for intervals greater than the critical bandwidth, which, as we will see later, in the case of the note A4 is about 130 Hz. The fundamental components of this spectrum are constituted by the tonic F4 of frequency F0 equals 440 Hz and its octaves F5, A6, A7, A8, with frequencies of the form 2 to the n by F0. Remember that the notes related by octaves form a class, in this case the class A. Each harmonic multiple of an odd number produces a new class of notes. Therefore, the tones produced by musical instruments generally have a pleasant sound and great harmonic richness. Next, we show the spectrum of the tone E5, which forms a perfect fifth interval with the tone A4.
The observation of the above spectra leads to the following conclusions. The harmonics of the fundamental of a complex tone constitute an important part of its spectrum, since they are among those with the greatest amplitude. There are other components of appreciable amplitude, which can be identified as notes of the diatonic major scale corresponding to the fundamental, tonic. Harmonics tend to decrease in amplitude as the frequency increases.
In order to identify similarities, we will next present side by side the harmonic series for the tones A4 and E5. Note that the harmonic series for the tone E5 generates the same sequence of degrees as the harmonic series for the tone A4, and that both have discrepancies with the frequency values in just in tempered tunings for the perfect fourth and major sixth. In other words, the harmonic sequence has a general format. Therefore, for the purposes of studying consonance and dissonance between other pairs of tones, it is not necessary to generate new spectra. Next, we provide a series of tables that summarize the process of calculating dissonance in intervals consisting of two complex tones. We'll begin with a table showing the process of calculating the beat frequencies between the different pure tones corresponding to the first six harmonics of the complex tones A4 and E5, which constitute the perfect fifth interval with the fundamental note A4. The light green central section of this table shows the frequencies of the beats between the pure tones that make up the harmonic interval A4-E5. Note that the arrows indicate that the 3520 Hz frequency of the third octave of the tonic F4 of the complex tone A4 is given by the difference between the 3960 Hz of the B7 of the second octave B7 of the fifth degree of the tone E5 and the 440 Hz of the tonic of the tone A4. Using the diagram described, you can explore the conformation of the rest of the notes produced by beats. Next, we repeat this table, but we replace the beat frequencies with the names of their corresponding musical notes. Hyphens are used to indicate that there is no beat, and therefore no additional note generated, for pairs of identical pure tones. It is revealing to identify in the spectrum corresponding to the sum of the two complex tones that constitute the interval, the new notes that appear in the beat and are not contained in the six harmonic series corresponding to A4 and E5, such as the notes A7 and G7. In this spectrum, the new notes provided by the beats and not contained in the six harmonic series corresponding to the tones A4 and E5 are indicated in green. Note that the note A3 has a frequency of 220 Hz, lower than the lowest frequency contained in the complex tones that constitute the interval, the note A4 of the complex tone A4. The other key piece of information required to determine the degree of consonance between the different pairs of pure tones that constitute the two complex tones is to determine the fraction of the critical bandwidth that represents the beat frequency of these two pure tones. We will now deal with the calculation of this fraction x. Let's return to the table of beat frequencies between pairs of pure tones. To evaluate the consonance and dissonance between pairs of pure tones, each belonging to one of the two real tones that constitute the interval, it is necessary to be able to determine the value of the critical bandwidth corresponding to the lower of these two pure tones. To do this, we will use a piecewise linear approximation of the critical bandwidth versus frequency graph provided in the article La Perception Acústica. Física de la Audición, Acoustic Perception, Physics of Hearing, whose link is provided in the description. Next, we will consider two cases for determining the critical bandwidth. The first case corresponds to the 3520 Hz beat between the B7 of 3960 Hz and the A4 of 440 Hz. In this case, the lowest frequency is 440 Hz, so the critical bandwidth must be calculated for this frequency, which turns out to be approximately 130 Hz. The second case corresponds to the 1540 Hz beat between the B6 of 1980 Hz and the C#7 of 2200 Hz. In this case, the lowest frequency is 1980 Hz, so the critical bandwidth must be calculated for this frequency, which turns out to be approximately 294 Hz. In the following figure of critical bandwidth versus frequency, these two calculation sequences are indicated by arrows. Next, we will consider the determination of critical bandwidth fractions. Below the table of frequency differences, beat frequencies, between pure tones, a table has been added indicating the ratio of frequency differences to critical bandwidths for each of the pure tone pairs. Arrows have been used to indicate the sequences for determining the ratio of frequency differences to critical bandwidth for two pure tone pairs. For the B7 and A4 pair, there is a frequency difference of 3520 Hz and a critical bandwidth of 130 Hz, corresponding to the A4, lower frequency, at the bottom of the difference table. The ratio between these values is given by the value 27.08 indicated in the bandwidth fraction table. For the B6 and C#7 pair, there is a frequency difference of -220 Hz and a critical bandwidth of 294 Hz, corresponding to the B6, lower frequency, on the right side of the difference table. The ratio between these values is given by the value -0.75 indicated in the bandwidth fraction table. Next, we will use the Plomp and Levelt curve of consonances and dissonances between pure tones to determine the degree of dissonance corresponding to each of the pairs considered. It is easy to see that the first pair has zero dissonance, since the fraction x equals 27.8 is much greater than 1. On the other hand, the fraction x equals -0.75 corresponding to the second pair indicates that it produces a dissonance of approximately 0.19. Calculating dissonance from the critical bandwidth fraction is the fundamental calculation of the proposed method and must be performed many times. Running it graphically on the dissonance curve we just provided helps to visualize it, but it is more convenient to run it numerically. For this purpose, a polynomial approximation of this curve was generated. Next, we will add a dissonance table to the description of this dissonance calculation procedure. Note that consonance is the ones complement of dissonance. We will highlight this fact by placing side by side the consonance table and the dissonance table. We have prioritized calculating dissonance because it is generally desirable to avoid it, and because it is important, as we will see later, to introduce tension and resolution into the tonal composition scheme. However, since the values of consonance and dissonance for pure tones are complementary to 1, it is trivial to obtain the table of consonances from the table of dissonances, and vice versa. Note that in the legends of these tables, we have added averages as an alternative measurement to the sum proposed by Plomp and Levelt. We could also have proposed percentages. Next, we present the set of dissonance tables generated for the interval studied, and we reproduce each of them so that their degrees of consonance can be appreciated and compared orally. This is something you should pay close attention to. Note that these tables are presented in the order of the degrees of consonance of their respective intervals. The screen shows side by side the Plomp and Levelt results for the consonance of complex tones for the octave from C4 to C5 and the results for the dissonance at the peaks that we calculated in the octave from A4 to A5. Although there is no coincidence of values, since different bass notes were used and the critical bandwidth values do not necessarily coincide with those used by Plomp and Levelt, since they do not provide this information and limit themselves to expressing that the critical bandwidth is approximately 20% of the tone frequency. The order of the degrees of consonance and the results obtained in this video for the intervals that have the fundamental note A4 coincide with the order of those indicated by Plomp and Levelt for the intervals that have the fundamental note C4. An important omission in the dissonance graph for complex tones presented by Plomp and Levelt is that it does not show information corresponding to the major second and major seventh intervals, which would complete the major scale. These authors indicate that this is due to the fact that only 6 harmonics were used, and that information corresponding to other intervals will become present as more harmonics are used. To verify this fact, the necessary calculations were performed to observe how the dissonance curve changes in the frequency range from the note F♯5 to the note A5 as harmonics are added. The result is shown next. It is observed that for the 7 harmonics, the contribution of the note G5, corresponding to the minor seventh, makes its appearance, which was to be expected, since this is the 7th note that appears in the study of the harmonic series corresponding to the spectrum of the complex tone A4, as the 7th harmonic of this fundamental note, as shown in the lower left corner of the screen. The changes that occur in the dissonance curve when adding the 7th harmonic can be explained by observing the dissonance curve for a pure tone, in this case G5. Note that in this case there is zero contribution from this harmonic at the frequency of 770 Hz, corresponding to the zero of the x-axis, so the curve approximately maintains its value at this frequency. The small variation it undergoes is due to the rest of the harmonics. From this value of 770 Hz onwards, the pure tone contributes to a rapid increase in dissonance on both sides of this frequency. Next, we will show the tables corresponding to the calculation of the dissonance at the frequencies of 770 and 780 Hz. One of the virtues of the method proposed in this video for calculating dissonance is that these tables not only provide us with the value of dissonance at a given frequency from the fundamental, but also show the composition of this dissonance. Although the method proposed by Plomp and Levelt is an excellent basis for attempting to generate a measure of the degree of consonance of a musical interval, it requires modifications in order to achieve this goal. The most important objection to the graph generated by Plomp and Levelt is evident in the result of our investigation of what happened in the frequency interval from F♯5 to A5. As the number of harmonics increases, the amplitude of the dissonance curve increases, since the dissonances corresponding to the added harmonics are added. This gives the impression that the dissonance curve will go down, but note that the dissonance for the octave interval remains approximately zero. This is because Plomp and Levelt considered pairs of pure notes of equal amplitude, which, as the spectra provided in this video reveal, is not what is real. Therefore, the decrease in the amplitude of the harmonics must be considered as the frequency increases, so that the graph will tend to a limiting amplitude. However, the proposed modification poses a difficulty, since the amplitude of the harmonics varies for each instrument and the way in which its notes are activated. The measure of dissonance depends on the type of instrument and its execution. This difficulty could be overcome by choosing a possibly ideal reference instrument. This video presents a detailed and in-depth look at how consonance and dissonance are generated between complex tones produced by musical instruments. The use of tables for calculating dissonance using the method proposed by Plomp and Levelt is very useful in visualizing the formation of dissonance and facilitates modifying this method to consider the attenuation that naturally occurs in the harmonics of these complex tones as their frequency increases, information that must be incorporated into these tables. As in the article by Plomp and Levelt, the second and seventh intervals, which play an important role in harmony, were not considered in this video, but the dissonance of these intervals can be determined using the same procedure used in the study of the incorporation of the 7th and 8th harmonics. However, according to the sequence of new note classes in the harmonic series, this implies the addition of the 9th to 15th harmonics, which represents extensive calculations. The knowledge gained in this video will be of great help in understanding harmony, musical composition, and how to vary the playing of an instrument when performing these compositions. Thank you for watching this video. We hope you enjoyed it and find it useful.